蔡维峰老师 from Taiwan State University, 中山大学 to come and give us this stage seminar. Professor Tsai did his undergrad and master's both here at NTU, and his master's advisor was in India. And then he went to UCLA and received his PhD in 2008. So, same as me. Not the same year. But before he received his PhD, he spent roughly a year at Stanford because his supervisor went to Stanford. And after graduation, he did a postdoc term at Purdue, and then spent half a year at the Solid State Institute of Tokyo University. And in the spring semester of 2011, he returned to Taiwan and became an assistant professor there. And today he's talking about Dirac surface states and topological crystalline insulators. Okay, Wei-Feng.
Thanks. First of all, I would like to thank Professor Ho and Professor for the invitation to give me an opportunity to give a talk here to share with you about our recent works. So today I'm going to talk about Dirac surface states and topological crystalline insulators. And let me. Before my talk, I would like to first thank all my collaborators on this subject. As you can see, there are a lot of people. I think in particular, I would like to thank my student, the National Science University, Chen Yi Huang, and also Professor Sun Ling, who is my long-term collaborator on this subject about topological insulators. Okay, and of course, it's also very glad to collaborate with several great experimentalists like Professor Hassan in Princeton, and also Vidya Medhavan in Boston College. Okay, so here's today's outline. First, I would like to introduce this new family of topological insulators called topological crystalline insulators. Well, the main question in this topological crystalline insulators, or this new family, is that I'll try to show you aiding an extra crystalline symmetry can lead something different. And next, of course, we are wondering if there's any real material which can behave like topological crystalline insulators. And indeed, there is. It's an old material, but in fact, it has new discovered physical properties. So that example is Tintera. And in today's talk, I'm going to introduce its bulk topological invariant in this material, its surface states, and many interesting properties in these surface states. Also, I want to mention some of our recent works in collaboration with experimentalists. And finally, I'll give a quick summary. Okay, so first of all, I would like to put my talk into a much broader context. That is, as you may know, that nowadays it's quite popular to find out a material called Dirac materials. This kind of materials is basically defined with Dirac-like linear spectrum. And due to this property, in fact, there are several consequences. one of them is that many physical quantities then scale in some way due to this linear spectrum. So let me give you some examples. In fact, so far there are many examples, various examples in various dimensions. For instance, in one dimension, we have carbon nanotubes. And as we know, they do have linear-like spectrum. But this is in 1D. And also, in 2D, there is a famous example, graphene. And also, today's focus, topological insulators. But notice that in topological insulators, although I'm talking about 2D Dirac spectrum, but in fact, topological insulators, I mentioned here, is a 3D material, but we focus on its surface state. Okay, and also very recently, people even predict there are so-called three-dimensional analog of graphene. So they call that the Dirac semi-metals, but this is almost the same meaning of graphene. We have a linear spectrum. So if in graphene, if you know a little bit about graphene, you know the spectrum can be expressed as k dot sigma. Here you do have k dot sigma, but in 2D you have sigma x, sigma y, but here you have whole set. You have a complete set of Dirac matrices. Okay, so today, of course, I'm going to focus on topological insulators. So I have to give you some sense of topological insulators. So first, let me give you some working definition for this this kind of insulator. First, we simply talk about for a topological insulator, actually, we mean, okay, we consider a single fermion Hamiltonian. We don't talk about interacting system, okay? And second, it must be, it is an insulator. So that means it has a gap in its spectrum. Okay, and then why it's different from trivial insulator? Okay, so this is a very nice definition. If you want to make sure topological insulator is non-trivial, then what you can do is you try. If you are doing first principle calculation, I think this is doable. You try to separate atoms as far as you can, and see if you the gap is your of your system becomes capitalized or not. Because if the gap doesn't close, then that means it cannot be adiabatically connected to the atomic limit of your system. So, in other words, this is the non-trivial case, and that's why we call it topological insulator. Okay. Of course, for experimentalists, this definition, working definition, I think is good for theorists. But for experimentalists, maybe we can use these alternative definitions. That means, for topological insulators, they have robust boundary modes. Okay, this is a good definition because you can simply try to observe or measure in the experiment for the boundary modes. Or there is also another working definition, but maybe we have to consider entanglement spectrum. This is another issue I'm not going to talk about today. Okay. So, as I told you in the last minute, we can define topological insulator as a system which cannot be adiabatically connected to atomic limit. But why we so that means it's non-trivial, of course. But why call it topological? I have to explain for you a bit. Okay. Actually, when we talk about topology, that means that's the topology of wave function. And in many cases, we simply consider we transform the system into momentum space, and topology is actually occurs in this momentum space. Let me take the famous integer quantum Hall as an example. Actually, integer quantum Hall system can be viewed as a topological insulator, but break time reversal signature because it has several similar features as topological insulator. Okay, by me, okay, topological insulators here I reserve for systems with time reversal symmetry. Okay, all right. But here I use integer quantum Hall as an example because I want to explain why I use the term topological. Okay, so for integer quantum Hall insulator, it has a Bok gap. As you may know, you have lambda labels. There is a gap there. And the second thing is, in this system, actually you can compute a non-trivial topological index called Stern number. Actually, this formula is quite similar to Gauss-Bonnet formula if you are familiar with topology in mathematics. And this is in some sense is similar to Gaussian curvature, and it's defined by this very vector potential. Actually, this is a block wave function. Okay, if you define this very vector potential, and this just similar to conventional electrodynamics, you can get F from A, and you do a momentum integral over the whole Brazil zone, then you will get the integer number. And this integer number actually corresponds to the whole conductivity sigma x1. Okay, so
what's the UM?
UM? Yeah. M is actually band indices. And actually this is this broad wave function is of course the eigenfunction of Hamiltonian. Okay, so UM is actually eigenwave function for n band.
So each eigen level, okay, has a different A, right? Is it?
That's true. That's true. But so here let me okay. So it's safer that I should sum over all different occupied bands.
Okay.
It's safer to do that. Okay, so let me give you a simple picture. Actually, if you consider a system with non-vanishing Chern number, a physical consequence due to bulk edge correspondence is that at the edge there are Gabriel's boundary modes. Okay, actually I'll talk about this bulk edge correspondence more later. But I just want to give you a quick picture. So if we have bulk topological invariant, then its physical consequence is that there exists a Gabriel's boundary. Okay, so once we have this integer quantum Hall picture, then we can quickly move to what the two-dimensional topological insulator is. Okay, this is the simplest picture we can have. If we take two copies of integer quantum Hall system, and one for spin up, one for spin down, and we make these two systems with opposite Chern numbers. Then we try to combine it together, and this is the simplest picture of two-dimensional topological insulator. Why this is the case? First of all, we see, as I said, a topological insulator has time reversal symmetry, but for a non-vanishing Chern number, we need the system to break time reversal symmetry. So here you see, indeed it has 0 total Chern number, because this is 2n plus 1 is minus 2n plus 1. So if you add them up, you get 0. So this is correct. However, there is another non-trivial, but this is still non-trivial, as you can see, because say if we focus at this from H, and what you see is that you still have Gabriel's propagating mode. Okay, and as you can expect, since you do have some non-trivial Gabriel's boundary mode, it suggests its bulk is also non-trivial. That means it possesses some kind of topological invariant. So for this two-dimensional topological insulator, or even three-dimensional topological insulator, we do need some other topological index to distinguish them from the trivial insulators. Okay, I'll talk about the topological index for topological insulators later. But here I give you some real examples. So as you can see, in real world, actually, we do have a two-dimensional topological insulator. This is the first case of that. This material is actually the heterostructure of mercury telluride done by Germany's group. In 2007, they showed that from transport experiment, there are contributions. And since we know it's an insulator, but we still have this finite conductivity, and therefore it must come from the edge state. So this is the first evidence for two-dimensional topological insulators. And also we have three-dimensional topological insulators. Here I give the example of bismuth selenide, which was done by Hassan's group in 2009. And here you can clearly see you have conduction band here, bulk valence band here, and the state surface Dirac constant. Okay, so this is an evidence for trivial topological insulators. And let me point out two important features for topological insulators. First of all, so far, all topological insulators actually are driven. Well, I should say it is closely related to band inversion phenomena, and this band inversion is actually induced by large spin orbital coupling. Okay, so and the second feature is that they do have time reversal symmetry, and due to this symmetry, we have Cramer's degeneracy and time reversal invariant momentum, and also because of this reason, that's why we have Dirac points on the surface, but they occurs at time reversal invariant point like gamma. Okay, so I promise I would like to talk about more about topological index. So next I'll go back to see it again. If we consider a system not only with time reversal symmetry but also with inversion symmetry, then the new topological index called Z2 index can be largely simplified. Okay, and the formula is simply looks like that. Look like this. Okay. Actually, it's simply a product of all parity eigenvalue at time reversal invariant momentum at all time reversal invariant momentum in the first Brazilian zone. Okay. And of course, again, just like when you compute the Chern number, you just count the occupied bands.
Sorry.
Yes.
What this inversion symmetry means spatial, real space inversion symmetry?
Yes, spatial inversion symmetry.
Oh.
That's right. So you will have, you will transform your state from K to minus K, but spin up, still up. So this is the spatial inversion symmetry.
So when we don't have the spatial inversion symmetry, we cannot use this Z2 invariant to classify non-trivial topological phase or trivial topological phase?
No. No, actually, the inversion symmetry here plays the role of simplifying the formula. Actually, there is a more complicated formula for this Z2 index. The index here is new. Okay, as you can see, because it's at the exponent, right? So it can be even or odd number here. So it has Z2 nature. So this new here is actually our Z2 index. But this formula, as I said, I emphasize this is only true if in your system you do have time reversal, both time reversal symmetry and inversion symmetry. However, it is not necessary to have the inversion symmetry for topological insulators. Without inversion symmetry, you still can define Z2 index.
So, so it means the left-hand side of the equation,
yes,
Z is Z2 invariant, Z2 index.
对
Z2 invariance still can exist when brokering the inversion symmetry, but when we broker the inversion symmetry, the right-hand side of your equation is more complicated.
Exactly.
Okay.
Exactly. Because then if you don't have emergent symmetry, then you do not have parity eigenvalue, right? It's meaningless.
Okay, thank you.
Yeah, but if you are interested in looking at more complex formula, I'll talk to you later. Now, I want to talk about more about Quark age correspondence in this case. Okay, you might wonder, why we do have gapless boundary modes, and in topological in a topological insulator, you may rewrite this system as a Dirac in terms of, or you can express the Hamiltonian in terms of Dirac matrices. And you'll find out that the gap of this system is provided by this Dirac mass term. And this is the only mass term in this time-reversal invariant and the inversion invariant system. And therefore, the parity operator, which is just gamma 0, it's equivalent to the Dirac mass of this Dirac theory, and the parity inversion. Okay, it simply means the sign change of the mass. For instance, if you have an insulator with conduction and valence band, and they have separate parity eigenvalue, if now during some process, for instance, you increase spin orbital coupling such that the parity eigenvalue inverse, then this is what I mean, band inversion. And also, this means the sign change of the Dirac mass. Okay. If this happens, then there must exist a boundary fermion mode, because this is simply a high dimension analog of Jacobi-Revy bounds there, okay, at domain 1. So for one-dimensional Dirac theory, if the mass changes sign, for instance, this is mass and this is x, and there is a boundary at this point, this is 0. Okay, and if your mass from positive to negative at the boundary, then and you can prove that it must exist a 0 mode at the boundary. So I hope if you are familiar with Dirac one-dimensional Dirac theory, maybe you can understand, you can realize topological insulator has similar physical form. Okay, so then we can proceed and ask, can one expect more from the other crystalline symmetries? So far we consider emergent symmetry. Okay, this is a discrete symmetry of the system, but you can say it's also one kind of crystal symmetry. But actually, we can get more. This idea is actually first proposed by Professor Liang Fu in MIT. He considered a system with time-reversal symmetry. Of course, first of all, we consider insulator. Okay, and this insulator is structured